absolute pleasure to be here. Again, thanks to Goodness for choosing such a beautiful venue. I will spend my 10 minutes trying to tell you a little bit about SAMI. I need to start off, of course, thanking the huge SAMI team who have done so much, many people in the room. Something I will particularly point out, Julia Bright, who some of the work I will show is hers in particular, and who's done an amazing job working on some of the instrumentation aspects of SAMI. So for those of you who don't know SAMI, and shame on you if you don't, but anyway, SAMI uses a 1 degree field of view on the AAT. In that 1 degree field we have 13 IFUs, so we're able to do a multiplex of 13 or 12. In fact, we put one fund on a calibration star, and then we feed those fibres to the AAT's A-omega spectrograph. One thing I really want to point out about sort of comparison things like Khalifa with things like SAMI and of course Mango, it's just that we're doing different things. So, I mean, Khalifa, the spectrograph that Khalifa uses has 300 odd fibres and it goes to one galaxy at a time. Now, SAMI has approximately twice as many fibres, but of course we're spreading those over 12 or 13 objects, so we really have much lower spatial sampling than something like Khalifa. So they're very, very complementary. We're trying to do different things here. SAMI and Mango are really about trying to do things where you need large, really large populations. So the SAMI survey started in March 2013, and currently we observe just over 1,700 galaxies. I can describe it all in detail, but I won't. I mean, the main thing I guess I will highlight is the fact that the regions we target are largely the gamma survey regions, and there's a really, really good reason for that, which is that the very deep and complete spectroscopy in those regions gives us beautiful environmental measurements. Right? So just an example, of our SAMI galaxies, almost 60% of them end up in the gamma groups catalogue. If we were to use a shallower group catalogue, say from the normal Sloan, original Sloan survey, only 15% of the galaxies would be in that group catalogue, simply because you haven't got this really deep spectroscopy. And so, to define environments really, really well, gamma is a beautiful resource. So I'm really, really sort of strongly saying gamma, just SAMI, gamma's fantastic. Just to give you a sense of the data, here, and you'll probably want to come to the front and squint at this to see what's going on properly, but here's just H-alpha maps in a star formation versus stellar mass plane, so the star forming main sequence, for roughly a third of the current sample. This is work largely due to Itching Ho, who's been done a huge amount of work on the data pipeline, particularly the emission line pipeline, SAMI. But of course, that's just H-alpha maps. It's also interesting morphologies and fun stuff you can see in there. But then you go to kinematics, of course, and you have that as well. And you can also take line ratio. So here's the N2 over H-alpha maps. And again, I'm going to spend hours staring at these sort of things and trying to figure out what's going on. This gets to the point of individuality that I'll try to touch on in a minute. Obviously, you see mathematicity, but you also see AGN, and you see evidence of winds outflows just in this slide. I guess what I'm really trying to get at, which touches on something Jakob said about us not targeting individual objects, but actually going to the full population, is that I wonder whether you can do both at once. It's not trivial to do, but I think we need to think about that. So this is the question: what drives the uniqueness of galaxies? Right. So apologies to anybody who knows the 1960s TV show The Prisoner. I'm not a number; I'm a free man or a free galaxy. Maybe pass by some of you. We know there's a whole bunch of things we know drive galaxy formation, galaxy properties. Things like stellar mass and halo mass and environment are certainly some of the things on the list, but there's a whole range of other things as well which we're just starting to get a handle on. We know, for example, that sort of the stochastic merger and accretion history of galaxies must be important. Right? If you look at any individual environment and mass spin in the galaxy population, you still see a huge range of galaxy properties. The question is, how can we capture this at the same time as being able to capture the full population? So can we have our cake and eat it? Probably the buffet. So, again, touching on, I think maybe something Stefan said, I mean, the scatter. We need to embrace the scatter. Right? The scatter is where most of the physics is. So I'm just going to try to touch on a few issues around this question of how we get at merger and accretion history. So there are various ways of doing this, of course. Some beautiful examples here. This is we've had deep imaging from a few years ago of early type galaxies, and you see all this amazing structure as you look at galaxies in detail. Another way of looking at mergers is via pairs, and I'm sure we'll see Sarah Ellison talking more about this later this week, where you can really see what's going to happen to galaxies and what the interactions between nearby galaxies actually do to their properties. But I've used actually open up, because of the kinematic measurement primarily, open up a new view on our ability to understand accretion and merging. So one way of doing that is simply by looking at the disturbance in galaxies. So here's work by Jeff Bloom, who's a Sydney Uni PhD student. Here we're just looking at the asymmetry in the velocity maps and the asymmetry in the velocity dispersion maps in a bunch of different galaxies. Well, I don't want to take too much away from this. The point is you can do this. The red points here are things that by eye look disturbed on a simple image, like just a simple slow image. And so these things that look disturbed, indeed, are dynamically disturbed. And so you can use this as a measure of galaxy interaction in a much more direct way, because you're seeing the dynamical effects. Right? You're not just seeing an odd-shaped galaxy, you can actually see the dynamics in play. Another way you can do this is looking at misalignment between stars and gas kinematics. So this is work by Julia Bryant. Here we've got a fraction of galaxies that are misaligned, so that their kinematic PAs are offset by more than 30 degrees versus morphological time. So this has been done before with the Atlas 3D team, so Tim Davis et al. This for early type galaxies. But if you just look at these blue points, which are the field and grid galaxies from SAMI, from ellipticals to late spirals, ignore these ones at the end there, just not well determined morphologies, you see a strong, very, very strong trend as you go from early type to late type. This is not surprising. There's a whole bunch of questions related to this. Is this just because the gas more quickly gets realigned in late types? Is it possible that the early types, because the gas stays misaligned for a long time, actually gives us a real view of the accretion onto galaxies? More than just a snapshot, we have a longer timescale picture of that. There clearly are differences in morphology, this strong trend in morphology. It's trends in the environment, well, this is a little noisy, the cluster galaxies we haven't got quite enough yet. Clearly cluster environment is important, but maybe not as important. A different view of this is to actually look at the stellar gas misalignment along this axis, morphological type on this axis, and so then you can see exactly what the misalignments are. And so a few things pop out of this. One is that there is an enhancement, it's significant, although, again, we always want more galaxies. There's a number of galaxies that are kinematically misaligned, but counter-rotating. These are 180-degree misaligned. So these are things where you've got the gas rotating one way and the stars rotating in exactly the opposite direction. And then you've got a whole range of things in the middle, except that if you go to the late type spirals, there isn't anything in the middle. Okay, now again, that's not surprising. There's two reasons why this could happen, and we need to figure out in detail why that is. One is that the time to settle for the gas to be torqued down onto the disk depends on the shape of the potential. With a more disky potential, it will bring it down more quickly. The other thing, of course, is if these late type spirals already have gas in them, then you will have that gas interacting with any infalling gas to also speed up that process. So there's some really nice modelling by Tim and Martin earlier this year, modelling the Atlas 3D early type to try to understand this distribution, both this peak at 180 and the distribution as a whole. I think what we need to do is to extend this to the full population of galaxies, not just early types. So I mentioned individuals, but I haven't really looked at individuals. And so just one or two galaxies. Here's one that has a 90 degree. So here's the stars rotating, here's the gas rotating in the opposite direction. I gave this galaxy a number, I should give it a name, because, you know, I've got a number of 3 galaxies, so I'm going to call this one Donald, because it goes in the 2 different directions at the same time, doesn't make any sense. Of course, there's many well, I won't dwell on that. So, in summary, I guess there's a few different points. One is that the SAMI data is there. There's already 100 galaxies publicly available. In July this year, we'll make another almost 1,850 galaxies available to the rest of the community with a whole range of high-level science products. I think we can have our cake and eat it, but it's going to take some thought. Okay, I think we can do both. We can get at this, the scatter, but it's going to be hard. And as I always said, we have these measurements of kinematic misalignments which point us towards merger history for some galaxies. So finally, I say embrace the scatter. Thank you. Can I have one more thing I just wanted to say, which is not a talk but a plug for a conference in Tasmania in about 6 months' time. If you like conferences on islands, slightly different island, please come to Tasmania. It's beautiful and you'll love it.
And in fact, many people in this audience will attend as invited speaker or participants.
Absolutely.
This lovely conference.
You can all come to Tasmania. Okay, sorry.
All right. Questions for Scott? Right here at the front.
MC from Swinburne University. I wanted to know, like, could you give me like a rough number of how many spirals have been observed with counter-rotating stellar and gases? Yeah. Sorry, it was probably on the slide. But
well, you can kind of see it here, but so these are individual galaxies. So it's not a lot, right? But there are some. It's a handful, less than 10 at the moment. This is actually using about half the sample we currently have. So there's going to be several tens in the full sample.
Great, thanks.
Maria, I can see you when you're ready. If you could come up to the front.
So why do you say it's surprising that in late types there's a lack of intermediate misalignment?
No, I don't think it's surprising. I think it's to be expected. Maybe I misspoke. I think what you expect is that any so two different things. One is the accretion could be different onto the early types and later types, but I think the default hypothesis should be the accretion is the same. It's just that you see the range here because the early types take a much longer time to settle. So here you both have a quicker settling time and probably have gas intensity.
So why would it not simply be that the intrinsic shape is different? Because if you have an axiomatic system, you cannot have stable rotation except for like coordinate counter-rotating, while early types triaxial you can. So
I guess that's what I mean. The gas can come in at an angle, but it will settle quickly, right? So that's that. There is a.
But Scott is not about settling quickly. In a triaxial system, you can have it stable over years. So it's not about stable.
Yes.
All right, we will take one more question while Maria can she be set up for her presentation? I don't know who's there to help. No. Anyone? And last question. Right. Okay.
It may be that so the regime of the accretion, the direction of the accretion defines the morphological type. We have found that the gas is counter-rotating in ventricular galaxies. We see star formation, and when the plane of gas rotation is inclined to the plane of the galaxy, we see shock-like gas excitation. So if you have the accretion in the plane of the galaxy effects, it stimulates star formation and forming of later morphological types.
It's possible. I think it's to some extent it is a little chicken and egg. We're not sure which one of these things is happening and driving the other at the moment. I agree. I think it could go either way.
Okay, we need to thank Scott once again.